can be done. So rotation, that's where we're starting. Got the recording going. It's one of the four transformations we're going to cover before our next test. A rotation is a transformation that rotates all the points of a figure around a single point, called the center of rotation. The number of degrees a figure rotates is called the angle of rotation. For our purposes, everything we're using 360 degrees is a complete rotation. Okay? Rotations, we said, can move clockwise or counterclockwise. Not a whole lot to write on here, so if I've underlined, I'd like for you to underline. So if the counterclockwise and the clockwise is confusing you, clockwise just means we go in the direction that the clock hands go. Counterclockwise means we go in the direction, the opposite, the hands that the clock goes. Okay? Right is clockwise. Left is counterclockwise, okay? We call translation a slide. We call reflection a flip. What would we call rotation? What are we doing? We're turning it, right? And would you think this is a rigid motion or a non-rigid motion? Yeah. Does it change shape or size? Do the angles change? They do not. So it is a rigid motion. So when we rotate figures, so we're going to look at this triangle ABC and triangle A prime, B prime, C prime. Pre-image and image, okay? So this triangle started out in that top left-hand corner and it wound up in the bottom left-hand corner. So it rotated 90 degrees counterclockwise or 90, 180, 270 degrees clockwise. Does that make sense? When we are rotating figures, we're rotating the image and we're rotating around the origin on the coordinate plane. So for instance, if we are rotating this image 90 degrees, we're going to rotate, and let's say clockwise. We're going to rotate the image 90 degrees, so that's a 90-degree turn, right? It's got four sides. Each turn is going to be 90 degrees. And we're also going to rotate it down to the next quadrant. The location in the quadrant does matter. I don't actually think you have to graph, at least not on tonight's homework. When you rotate around the origin, you're just going to pull it to the right spot, and it's going to place it on the correct coordinates in the correct quadrant. Does that make sense to you guys? So I placed this here, but you're going to basically have a handle where you can drag that figure around, and it's going to do all the rotating for you. But we should be able to recognize the rotation. So this is a 90-degree clockwise rotation. We wanted to do a 180-degree clockwise rotation. 1 quarter, 2 quarters. That's 180 degrees there. So they're opposite quadrants diagonally. So we're going to rotate the figure 180 degrees. That's 90. That's 180. And we're going to put that a little askew there so I can straighten it up. That's got to go down. 2, 1, 1, 2. Yeah. All right, so a 90-degree rotation. The figure rotated and the quadrant. 180-degree rotation around the origin. Right? These are all around the origin. The image rotates 100 degrees, and when it does, it moves to that other quadrant. And the last one, if we do a 270-degree clockwise rotation, that's 1 turn, 2 turns, 3 turns, 90, 90, 90, gives us 270 degrees. I think that would go there. Right there. So far, so good? Okay. All right. So for you, when you rotate the figure on Alex, basically you have a handle. You're just going to drag it around. But I wanted to show you here, 180 degrees. We're going to turn it 1, 2. Looks like theirs, right? Because this is the image, the pre-image. This is the image. And it's going to wind up, if I can get it rotated right. All right? That's not exactly right, but close. Yeah, I think that's about right. So once you rotate it, we've been doing these questions a lot. This has to do with whether or not, with the rigid motion or non-rigid motion, right? So if two sides are parallel in the original figure, those sides are parallel in the final figure. Is that true or false? Right. So rigid motion, none of that changes, right? The final angle measures are the same as the original angle measures. Is that true or false? True. The final side lengths are longer than the original side lengths. Is that true or false? Yeah. And the original figure and the final figure are congruent. That's true. So the position has changed, the location has changed, but not the dimension, right, or the size. All right, so this particular activity, it asks you to use the tool to move the solid triangle exactly onto the dashed triangle. And it's not going to be just triangle, that's maybe it's other shapes too, other polygons. If this is not possible, click on not possible. I just copied and pasted. I can't do that here. All of that here, it's the flipping that I can't do. But for this particular figure, you're going to drag it. You're going to flip it. You have the option to flip vertically or flip horizontally, and I think you're going to rotate, and then it will line up exactly on that triangle. Sometimes they won't, right? But these are all your options you have, and you can do any of them at the same time, except not possible, right? But you can move it, rotate it, flip it vertically, flip it horizontally. Same thing with this one. You're going to move, flip, and rotate, and just lay it right on top of that triangle. Unless you can't, and then you're going to click not possible. All right. Easy peasy so far? I do not think this is a particularly difficult section. Can it be difficult? It can, but I think if it's the stuff we're doing today is relatively intuitive. There are some spatial things that like we talked about. All right, so this problem looks a lot like other problems we did for translations and reflections. They give us a pre-image, triangle DEF, and an image, triangle D prime, E prime, F prime, and you need to transcribe the coordinates for the ordered pairs for D prime, E prime, and F prime. So you guys do that real quick. If you struggle with that, you should practice it. It's hard to do these problems if you can't write the coordinates for an ordered pair or plot a point. What'd you get, Kellen, for D prime? You didn't do it? Okay. What'd you get, Mayal? Say it again? +5, +1. Yep. What'd you get for E prime, Thomas? -2, +8. What'd you get for F prime, Morgan? 4 and 6. Good. All right, so just like the other ones we've seen, other transformations, we've seen similar problems. We've got to pick the rule. And they do this so we can see what's happening here, right? So we're looking to see, are the X and Y coordinates in the same place? And are they the same sign or opposite sign, right? That's basically what we're doing. Once again, we've done these for the other one. kind of transformations we've done. So 1 was the X, now it's the Y. 5 was the Y, now it's the X, but is it the same sign? It is not. So we've swapped the coordinates, and it's the opposite of the Y coordinate. Does that make sense? So which one of these options is it? Look through this left column here. Are any of these the appropriate rule? So this one. So let's call this 1, 2, 3, 4. One of these is the appropriate rule. The bottom one here. So this says that they swap places, which they did, but this says that the Y and the X switch signs, right? So that one's not it. And none of these have them swapping places, so those can't be right, right? How about this row? The top one, right? So they swapped, and the Y has the opposite sign. All right, so this is not rotation, but this is related to rotating, kind of. So we have to draw all the lines of symmetry. Do you guys remember what lines of symmetry are? We did the reflections, we talked about them. Are there any lines, imaginary lines, that we could draw through this parallelogram? So if we fold it over in itself, all the points line up. Say it again. Did somebody give me a suggestion? So we could do a vertical line through these two vertices. So if we fold, if this was a piece of paper, we folded this right side over to the left side, everything would line up, right? So that's a line of symmetry. Is there another one for this one? The horizontal? And now we couldn't do it here, right? That wouldn't work. But we could do it through those vertices, through those other, basically it's the diagonals, right? So you should draw those two lines of symmetry on yours if you haven't already. And you also do it for other shapes. And this is called reflectional symmetry. I say that we're going to be talking about rotational symmetry in a minute as well. All right, a regular pentagon is shown below. Suppose that the pentagon is rotated counterclockwise about its center so that the vertex at A is moved to C. So I underlined counterclockwise, and I underlined A is moved to C because this morning in second period, I tried to rotate it C to A, and it's not the same thing. Okay? I did counterclockwise, but I did not do it, the from and to were swapped, so that it was wrong. All right, so be careful on that. If you didn't underline it, let's underline it. So we're going to go from A to C, and counterclockwise is, remember this is counterclockwise. You start at the top and you go left. So I'm going to start at A. I'm going to go left 2 sides, right? Why did I pick 2 sides? Kind of like 2 turns. So when we're rotating this pentagon, we want to figure out how many degrees, what is the angle of rotation for each of these turns, right? When we rotate this, we're going to take 360 degrees and divide it by the number of sides. That will give us the number of degrees in each turn. So for this, it's 360 divided by 5. I keep wanting to say 120, but it is not 120. It's 72 degrees, right? So if I rotate this one side, that's 72 degrees. If I rotate it one other, it's 72. Say it again. Oh, you're right. I did the same thing. Well, I did the opposite thing. So I underlined it and still did it wrong. Oh, you're right. So that's clockwise. Yep. So this is, well, that's counterclockwise. Oh, but I did. Yep, I got to go the other way. You're right. All right. So, to learn from my mistakes. Counterclockwise is going to be this way. So how many turns? 1, 2, 3 turns. So it's 72 and 3 turns. So I think it's 216. Is that right? 216 degrees is how many degrees it's rotated. Yeah, so yeah. All right. So for each week, are we good with that? Any questions on that? Maybe my mistake helped you understand it better. That I make sure I wrote it the right way, but I wasn't starting at the top, right? So when we're thinking counterclockwise, maybe I should start where I'm going to start rotating from. So maybe I should have done it like that to give myself a little preview and maybe catch that mistake. Okay. For each figure below, determine it as rotational symmetry. So when we're looking for lines of symmetry, that's reflectional symmetry. Now we're talking about rotational symmetry. It says we're going to determine it as rotational symmetry, and what is that? Well, that is, can it be rotated and look exactly the same in less than a turn of 360 degrees? So if it does have rotational symmetry, we're going to give the smallest angle of rotation needed for the figure to appear unmoved. So if they're not going to let you rotate it on our spec just for us for the first part. Let's see. So this has 4 sides. You think we're going to do it in quarters, 90 degrees. That's 90 degrees. It's not lining up. 180, it doesn't line up. 270, it doesn't line up. It does not look like it started until we get all the way around. So that trapezoid does not have rotational symmetry. Does that make sense, Thomas? So does this pentagon? What do you think? You think it does? We just rotated it before, but we didn't talk about that. So this is, say, I say this is 1 turn, right? Would you say it has rotation? Does it look like it did when we started? So this one does have rotational symmetry, and we actually just found the angle of rotation. It's 360 divided by 5, which is 72 degrees. All right, for each figure, decide whether it has rotational symmetry, reflectional symmetry, both types of symmetry, or neither type of symmetry. All right, so you're not going to be able to rotate them, but I duplicated here so we can rotate. If I turn this 90 degrees, it doesn't matter when I turn it, it's not lining up. Would you agree? It doesn't look like it looked originally until we get all the way around. It does not have rotational symmetry. Does it have reflectional symmetry? Is there a line of symmetry there? There is not. So it has neither. For the star, see what happens when we rotate. When we rotate it, does that look like it did when we started? It does, right? In case you're not sure, they look exactly the same. So it has rotational symmetry. Does it have reflectional symmetry? Are there any lines of symmetry there? Definitely lines of symmetry. Draw a vertical line here, which will on the other half. There's both this upside down V or chevron, whatever they call it. There. Never looks like it did at the beginning until we get all the way back 360 degrees. Would you agree? Maybe I should rotate over here. Not until you rotate it 360 degrees. So it does not have rotational symmetry. Does it have reflectional symmetry? It does. If you draw a line of symmetry right down the middle, right? So it has both. This one was hard for me. All right, I can see the rotational. I'm going to show you guys. So a quarter, no, but at 180, it looks exactly the same, right? So it does have rotational symmetry. Does it have reflectional symmetry? I was thinking you could draw a line there and fold it in half, but you can't, right? Because the right side and the left side aren't going to line up, but that was hard for me to see. So we're going to say just rotational symmetry. See? Oh, it doesn't. It just has a reflectional. It just got split. That dot got split down. Thanks for pointing that out. All right. Any questions? All right. Do the figures have rotational symmetry? We talked about that. And do they have point symmetry? Point symmetry means it looks the same upside down. Rotate at 180 degrees, it will look the same. So we've already established this chevron does not have rotational symmetry, right? Does it have point symmetry? Well, let's see. If I wrote, well, if it had rotational symmetry, it would also have point symmetry. That's 180 degrees, so that's a no. No to both. Does this have rotational symmetry? This one does. Let's look at it. We can rotate it one angle of rotation, and it looks the same, right? So it does have rotational symmetry. And we've already found that one a couple of times. We're going to do the math again. It's 360 divided by 5. That would be 72 degrees. So will it look the same upside down? Well, this is right side up. Does it look the same upside down? It does not. So it does not have point symmetry. You can rotate this 72 degrees, 72 degrees, 72 degrees, and it's rotationally symmetrical, but not the 180. So far, so good? All right. Morgan, did you take your face out of your spreadshirt for me? Thanks. All right. I created a visual because this is a step that's hard for me to imagine. The trapezoid will be shown below. Line A intersects two vertices. Line B bisects each side it passes through. That's center point, and T is the center of the trapezoid. Which transformation must map the trapezoid exactly onto itself? So that means it's going to line up to polar across those lines, right? Technically, reflection is that, or when you're talking about line of symmetry, we are talking about reflection. If I swap all these points, that would be the reflection, right? So this is A. Would everybody agree with that? Looks like A from this. It's not exactly the same size trapezoid, but you get the gist, right? Diagonal there, right? If I fold it along A, let's look at that. Does that line up exactly? What do you think? Is B going to line up exactly either? No, but if I fold it on, it does not line up exactly, right? So that can't be it. What if we rotate it 230 degrees? Would 90. That's 180. And that's 270. So no go, right? Oh, I did the wrong way. I should have been counterclockwise. Oh God, I'm so challenged. And now, not only is it counterclockwise, I'm facing you. But you get the gist, right? Don't make my brain explode. Okay, 180 degrees. Doesn't matter which way to go. Thank gosh. It says clockwise, but counterclockwise and clockwise, if it's 180, it's the same thing. 1, 2. We're gonna just. It does not look the same, right? So this is none of the above. Okay? But they're not all going to be none of the above. You have to use your spatial sense, which I'm sure all of yours is better than mine. Okay? So we're not going to finish our notes yet. We're going to go ahead and start our homework. That way we can get some done before we leave. If you get done with it and you have a 100, you can scan and submit it in class.